Hi everyone, and welcome to this introduction to transistors, or more correctly, BJTs, which are bipolar junction transistors. Now there are actually a few types of transistors, BJTs being one of them, FETs being another, field effect transistors, and then there's variations of FETs like MOSFETs, JFETs and things like that. So for today, we'll look at BJTs, and another day we'll look at the different FETs. I've got a couple of examples of transistors here. This one is in a can or metal housing, and it's got 3 legs. Here's another one. This is actually in a plastic housing. So this would deal with probably a little bit lower current, less power requirements. Again, 3 legs. Now, a transistor is a semiconductor device. Just like a diode was a semiconductor device, but now we've actually got one more region. In a diode we had a P and an N junction. Now that we get to BJTs, we've actually got one more. So we could have something like that, or we could have something like that. NPN transistor or PNP. And we've got a connection there like that. So 3 connections. Now, in a nutshell, a transistor can either be used to switch, so switch high currents using a low power device, or it can be used to amplify. A good example of using it as a switch would be in a piece of digital equipment. So we might have a little microprocessor here, or CPU or something like that, and this might be programmed to drive a motor. So we might have a motor over here. Let's see, how do I draw a motor? There we go, there's a motor with a wheel on it, let's say. Now, we can't directly just connect the CPU straight to the motor because the CPU can't handle the current required by the motor. What we can do is we can connect the CPU to our transistor in such a way so the CPU will go to the transistor, it will turn the transistor on. When the transistor turns on, it can supply all the current needed or required by the motor to turn. So that would be a good example as a switch. Now, an application as an amplifier is we could have, let's say, a microphone. We connect the microphone to the input of the transistor. We then connect a speaker to the output. We talk into the input, which is a very, very, very small signal. The transistor will then amplify that to such a level sufficient to drive the speaker so we can hear ourselves talk. Now, another really good sort of analogy to have a look at is this. Let's actually use my pen. So I've got a pen here. Let's say I put a pivot point right here. So halfway would be there. I'm going to put my pivot point right over here to the left. Now, if I was to come along, and let's call this my input, if I was to push down on the input, let's say by a few millimeters, let's call this the output. The input has moved by just a few millimeters, but what has the output done? The output has moved quite a bit further than what the input did. So if I move this a millimeter, this might move by a centimeter. So it's actually amplified my input. If I move it the other way, let's move it by a centimeter or so, you can see the output has moved a much greater distance than what the input did. So as we get a signal coming in on the input that goes positive and negative, just by a little bit, you can see the output swings a lot more than what the input does. So a transistor is just like this. We have a small input, it will then amplify that to give us a big output, which is a representation of that input. Now, I've just told you that we had NPN type and PNP. The circuit symbols for each are just like this. This is NPN, Notice how it's got an arrow pointing out. PNP is like this. Oops. Forgot how to draw an arrow. PNP. Now there's a widely used little memory prompt for this, and that is for NPN we say it's not pointing in. For PNP we say points in perfectly. So obviously the in part of it doesn't actually start with N, but you kind of get the idea. So they're referring to the arrow. Not pointing in, NPN, points in perfectly, PNP. We have what's called the emitter, the base, and the collector. Just in short, the emitter effectively emits all of the electrons. So the electrons will start here. Some will go into the base. Most of them will go through to the collector, because that's where it collects them. The base controls how much current will go through will go through the device, I guess. So the more current we get going through the base, the more we get going through the collector. It's very similar to something like a tap. So you've got your tap there, and you've got all the pressure behind that tap. If you turn the tap on, you'll get some water flow through. The more that you turn the tap on, the more water you get going through. So the more we turn this device on, which is controlled by the base effectively, the more current we get going through the device. Alright, so the internal makeup. Since there are 3 sections to it, or 2 junctions, we can either create it so that we've got this type as N, this here is P, and this N, which would give us NPN. Or we can have the opposite. We can make this out of P-type, this out of N-type, and this out of P-type, so we would have PNP. NPNs are the most common, I believe. PNPs we generally use if we're going to have a negative power supply, or we use them in special amplifiers called complementary symmetry amplifiers. I'll just deal with NPN because it's by far the easiest to understand. Alright, now in order to create N-type material, we need to dope it with such a material to give us excess electrons. So the emitter region, which is here, which is the biggest region out of the 3, is heavily doped with electrons. So we've got loads and loads and loads of free electrons in here. The base is P-type. So it is doped to give us a deficit of electrons, which leaves us with holes. So it leaves us with positive ions, and there's only a few of them there. There's not many, as you can see, compared to the emitter. The collector is lightly doped with electrons. So we've got N, P, N, heavily doped, so loads of electrons, very lightly doped, so just a few holes, and in between these two, we've got a few electrons up here. Now, if you recall, in order to get current to flow in a diode like this, we needed to connect positive to the anode, or positive to the P, negative to the N. That would close the depletion region, and we would start to get current flow from negative to positive. Well, that stands true for the base emitter of our transistor. So I'll just represent this with a power supply. In order to get this thing to work, we need to forward bias or turn on the base emitter region. So we connect up a power supply, and if this was made out of silicon, we would need roughly 0.6 volts here to close the depletion region between the base emitter here. Once we close it, we will get current flow through here. At the moment, it's acting exactly the same way as our diode acted. We now have current flow. Now, we've got this collector up here. This, and of course we don't just connect it like this, but it's a good representation. The collector is going to have a positive potential on it. So we actually reverse bias the collector. if we reverse bias the collector junction here, we've actually got a depletion region. So if you recall from the diode tutorial, the depletion region is a high resistance region. Excuse me. So forward bias here, we've got current flow. We connect up positive to the collector with respect to the emitter, and we've got a reverse bias region. So it's hard for the electrons to get over here. Now, in a minute, I'll show you an analogy that I use with my students in order to get them to understand what goes on. But effectively, we've got all these electrons, loads and loads and loads of them. We get current flow, so all these electrons start getting pushed up into the base. There's hardly any free holes for these electrons to jump into. Therefore, we get very little current flow through the base. What we end up getting is a whole heap of electrons built up in this base region. So just pretend this power supply isn't there for the moment. We get all these electrons built up into the base region. They can't cross here because it's reverse biased. If we then come along with a positive power supply, and let's make it around 10 volts, connect it to the collector, we've now got a big positive potential on the collector. This potential will actually attract all these electrons that are stuck up in the base region. It'll attract them across the reverse bias region, and all the current will flow through the collector like that. If I was to put in a resistor here and make it variable, so one of those variable resistors like a potentiometer or something that you'd use for volume control, if I put in a resistor there that I can vary between, say, 100 ohms and 1000, I will actually vary the amount of current that goes through here, or I'll change the amount of current going through the base emitter region. The less resistance here, the more current through here, which means the more electrons get stuck up here. If I have that power supply connected here, it means the more current will jump across here. So you can imagine if all these electrons are all stuck up here, and we push them a little bit harder, they will actually jump across and we'll get loads of current flow through the collector. So a Bjt acting as an amplifier is something very similar to this. We forward bias the base emitter. We then put in a signal on the base which will increase or decrease the electrons going through the base, or the current going through the base, which then gets amplified through the collector. So let's have a look at this analogy and see how we go. Now, I'm going to need you to use your imagination with this one because it is quite interesting. Now, to try and get you to understand how the internal workings of this work, I'm going to use this analogy. So, picture that we have a room. So there's a room up here. Let's see if I can draw a room. Just like this. So we've got a room. We then have a cliff. So there's a cliff sort of going down here outside the room. Now picture this room is filled with people. So lots and lots and lots of people. And it's as full as you can get. So it's just chock-a-block full of people. Alright, so this room is the emitter. So just picture filled with people. This is a room. They can't get over the walls or anything like that. They're just inside that room there. We've got this cliff down here, and we've actually got another cliff on the other side. So it's a bit of a chasm or a canyon, whatever you want to call it. Now, we do have a little hole down here in the side of the room. Alright, so this is the emitter here. Picture this as the base. This little hole is the base. We have a Grand Canyon here, so picture that as this reverse bias region here. Now, this is where we start to use our imagination a bit. picture this wall back here, this back wall, picture that this is moving forward. So the room is getting smaller and smaller because the wall is moving like this. What's going to happen with all these people that are filled in this room? Well, all the people are going to try and climb through this hole here. If this is moving this way, people aren't stupid. They don't just want to jump down this canyon because they'll die. So they're going to try as fast as possible to get through this hole. How many people do you think you'd fit through that hole in a certain period of time? Obviously not many. So we get only a few people actually escaping through here. We're going to end up with loads and loads of people right here on the edge. So the room's filled with people, this wall's moving this way, so that's our current flow. We get just a few people escaping through this little hole. They don't want to jump down here because they'll die. Alright, now picture that we come along to the collector with a big positive potential. So the collector is like the other side of the cliff or the canyon here. Now remember, use your imagination, picture this is a huge vacuum. So we've got a massive big vacuum over here. If we turn on this vacuum cleaner, let's say that now all these people have to do is just jump and the vacuum will pull them across. So we've got loads of people lined up here. All they now need to do is jump and the vacuum will suck them across this big massive canyon. So we're going to get loads and loads and loads of people jumping across here like this. If we were to increase the base current here, so if we were to turn this resistance down a bit, we're going to increase the current flow. So that means that this wall now moves faster. If that wall is moving faster, we're pushing the people faster, so we're going to get more people jumping across. So I hope you've been using your imagination. That's kind of my explanation for how the internal workings of the transistor work. So we have the base, emitter, and collector. In order for this thing to work initially, we need to forward bias the base emitter by connecting up a battery positive to the base with respect to the emitter. That will give us current flow. The more current we have flowing through here, then the more we're pushing these electrons up and they get caught up here. Now when we apply a positive potential to the collector, it actually has an attractive effect and it pulls all these electrons across this reverse bias region. So a little bit of current flow here results in a big current flow across here, because as you can see, only a few electrons at a time can get through this little gap, but a whole heap of them can go across here. If we were to increase the current, so let's say we increase the current here just by 1 milliamp, we might actually increase the current through here by a factor of 100. So 100 milliamps. So if we have 1 milliamp here, we might have 100 through here. If we increase this to 2 milliamps, we might get 200 milliamps flowing through here. So it's actually amplifying what we're doing at the input. If we were to connect a microphone up to here or something like that, and we start talking into it, the microphone signal will be very small, but it will be amplified by a factor of 100, just for my example, a factor of 100 through this collector region. So we could connect a speaker to our output in a certain way, and I'll show you how to do this later. In a certain way we could connect a speaker to our output, and we could then start to hear all that lovely music coming through.
So to sum up, BJTs are bipolar junction transistors. They're a 3-terminal semiconductor device consisting of an emitter, base, and collector. We can produce a large change in the collector current by a small change in the base current. Stay tuned for more tutorials including transistor operation in various circuits. You've been watching another Retro Brad video. Be sure to check out and subscribe to my channel for more electronic projects, hacks, how-to videos and tutorials. God bless.